All right, today we've got our first practice test. That doesn't happen until 2 o'clock, so we got some time. First, we're going to talk about Cartesian coordinates, also known as rectangular coordinates. This is where we don't just take one real number line, we grab another real number line and put it perpendicular. So we don't just have one real number line. That's boring. We put another real number line perpendicular to this one and have them cross at 0 because it would be really inconvenient to have them cross anywhere else. So the coordinate system is just two number lines perpendicular crossing at 0. That's way too small. This needs to be big. So it's just a number line. 0 in the middle, count positive in one direction, count negative in the other direction. And then we have another one going up and down. 0 in the middle, count positive in one direction, count negative in the other direction. It's just two number lines crossing at 0. Number lines have a direction. They have a positive side and a negative side. We tend to write our positive side as going to the right and our positive direction as up. We tend to count right as positive and up as positive. Not as value judgments. We just all needed to agree on something, and this is what we picked. We, like I was there. The way I indicate the positive direction, I just put a little arrow, and that's where I label it. So X is getting positive in that direction, Y is getting positive going up. What we are doing is just putting a grid onto two-dimensional space. This is just a grid for two-dimensional space. All we're doing is making a grid for two-dimensional space so that we can uniquely locate any point in two-dimensional space. And it works just like an address. How do you spell address? 2 D's, R-E, 2 S's? 2 D's and 2 S's? Like that? Fuck, that looks wrong, but all right, we trust you. There's certain words, no matter how I spell them, it looks wrong. Every variation looks wrong to me. I don't know why that is. It's like an address, except it's an address that actually works. We try to do this in like cities and shit because you have a number and a name for the street. The problem is like other cities also have those same streets and they're in different places. Also, it gets really inconvenient when the streets get too long. It's like on El Camino, there's like addresses like, what's your address? It's like all 24,378 El Camino Real. Like, oh, we need to partition this a little bit more. And they're like, oh, fuck no, keep going. What's your address? 5.78 times 10 to the 5th. I'm not suggesting that we just have one origin for all of addresses. Hold on. So all we're trying to do is make a unique marker for every point in two-dimensional space. And sometimes we do this locally. So the way we describe these points, in case you haven't seen it before, actually, even if you have seen it before, we still do it the same way. We list a horizontal location and then a vertical location. Horizontal one always go first. So we list a point. We list coordinates. Instead of saying address, we say coordinates. So this description is coordinates X and Y. We list the horizontal coordinate first, the vertical coordinate second, and we put them in parentheses separated by a comma. So this point here, if I drop down to the x-axis, it corresponds to a horizontal coordinate of 2 and a vertical coordinate of 1. Questions? Is anybody that's never seen Cartesian coordinates before? That's good, because if you had raised your hand, you'd be incorrect. You just saw Cartesian coordinates. And that was before I asked the question, which is technically correct, the best way. So we'll list an x coordinates and a y coordinates. These will correspond to horizontal coordinates and vertical coordinates. We'll usually just say x for horizontal and y for vertical. That's the most common thing. It doesn't have to be that way. If someone changes that up, they're deliberately trying to mess with you. So this x is the horizontal. And y is the vertical. Those two coordinates make one point. Any questions? Another way we can describe two-dimensional space, which I'm going to mention now, not because it comes up so often, but because I started in the habit of saying it, and so now I cannot stop. Another way to describe two-dimensional space, another way to abbreviate two-dimensional space is we might write R2. So instead of writing a regular R, you're going to write a double line and then finish the R regular. So double R. A double R like this means real numbers, and we have two real number lines, so we put R2. We write it as R squared. We say R2. Pirate spelling. We say R2 instead of R squared. The reason that what's going to trigger us to say R2 and not R squared is that the R has a double vertical. This is actually just called a double R when you want to type it. You look up how to type a double R. And it's an abbreviation for the real number line. A double R is an abbreviation for real numbers. How's everybody okay? We're all good because it's just the naming of parts. So when I talk about R2, I'm referring to two-dimensional space. And we will usually describe two-dimensional space with rectangular coordinates. This is not the only way we can describe two-dimensional space. This is not the only way we could describe R2. All we really need is two numbers. In this case, we've set up a horizontal and a vertical. They both represent a distance, so we're locating points with two different distances. This brings us to the question. This is trig class, dude, where are the angles? I'm like, oh, calm down, we are getting to that. And that's where the standard position stuff comes in. Any questions before we move on? Standard position. How's everybody okay? I'm just trying to gauge stress level because there's a test happening today and we're not doing it right now. And that's really annoying. It's like if I have plans at 5 o'clock in the evening, I can't get anything done before then. Unless I'm at work and I'm going to be leaving work and going directly there. If I'm like at home, it's like, oh, should I start laundry? I can't. I've got plans in 6 hours. I could literally get all my fucking laundry done in those 6 hours, but I'm like, oh, I can't, dude. I've got plans. I've got to, like, I don't know, stand around and not do anything before then. I think I'll have more coffee. That'll help. It never does. Then you get there and your friend texts you. It's like, oh, dude, I'm going to be late. And you're like, oh, I've been waiting 6 hours to do this. Sorry. Wait, what are we talking about? Oh, yeah. Neuroses is what we're talking about. So we need to bring angles into this. We need to take Cartesian coordinates and figure out where the angle's going to go. Standard position is about putting angles on the Cartesian coordinates. Actually, I don't want to phrase it this way. I want to say use angles for coordinates is really kind of where this is headed. So let's just phrase it that way. The big idea here is in standard position, we get a bunch of stuff out of doing this. This is very efficient. It's going to allow us to start doing trig functions with angles that don't fit into right triangles. So it frees our trigonometry from just the prison of right triangles. And it also is going to give us another way to describe two-dimensional space. We're going to use angles for coordinates. So we want to think of that as the big goal. Here is how standard position works. When we have an angle, there is an initial side and a terminal side. An angle has an initial side and a terminal side. Come back to it. An angle will have an initial side and a terminal side. So here is an angle theta, and I have put an arrow so we could say where the initial side is and the terminal side is. Spelled I wrong. Notice the angle also has some kind of direction. We start at the initial side and we go to the terminal side. Standard position does two things. Number one, we put the initial side on the positive x-axis. Number two, counterclockwise is positive direction. Well, vertex is at the origin. I didn't even mention the vertex. Holy cow. So the vertex is at the origin. The initial side is on the positive x-axis. The terminal side is wherever the terminal side is, but positive is counterclockwise. Counterclockwise rotation is positive. So there's how standard position works. You put the vertex at the origin, the initial sign on the positive x-axis, and counterclockwise rotation will be positive angles. Pause for copying. Oh, don't read that part. Yes.
So if it's going clockwise, does that mean you get sometimes still on the positive?
No, the initial side will still be on the positive x-axis, but if we're doing clockwise rotation, we would say negative degrees. Let's draw a picture of some angle in standard position. I should try to convince everybody to say this. You have to go R2. But the problem is I have Calc 3 right before this, and I say R2 and R3 all the time. So you'd be standing outside the door. It's like, well, how come you don't do it in calculus? I'm like, well, we stopped doing it in calculus. We have to do it in trig. And it just becomes even less believable than it already is. Let's look at some examples. Let's draw a set of coordinates, give ourselves some room. I'm going to start here. So I'm going to draw an angle that's going to be positive 45 degrees. We put our vertex at the origin. Our initial side is always going to be on the positive x-axis. And I'm going to rotate 45 degrees in the positive direction. I picked that because it's easy to draw. We just draw the line y equals x. There's an angle with 45 degrees. It's going to get crowded in the middle, so I might label this on the terminal side. This terminal side is at 45 degrees. That would be another option for labeling that particular angle. When I say negative angles, when I say counter or clockwise is going to be negative angles, that means if I draw an angle down here, if I go 45 degrees clockwise, I could call this angle negative 45 degrees. Because they're going clockwise, I can say negative 45 degrees. Negative 45 degrees. Counterclockwise is positive, clockwise is negative. Yes. We could be looking at angles that are in weird places, but in standard position, the initial side is always on the x-axis. So I might be interested in the angle that goes from the terminal side of the 45 over to, let's say, a 100-degree angle, and I could be concerned with that angle in the middle. But we could figure out how many degrees that is. But in standard position, this is what we want. This is how we're going to set it up. This is just for standard position, not just measuring angles in general. No, we can't have that, right? We just have to go further than 90 degrees. Yeah, we could have 180 degrees if we go all the way over to the other side. Good question. Is everybody okay? This is just how we're going to set up coordinates. Remember, we have to have like a 0, 0 point for setting up coordinates so that we're all working from the same place. But there is a distance between this 45-degree angle and say like a 100-degree angle, right? So if I put an angle up here, I'm going to do 120. No, I'm just going to guess. So maybe this angle is at 100 in standard position would be 100. It'd have to be more than 90. So I'm going to go with like 110. So I might say in standard position, this angle is 110 degrees. That makes sense because the positive y-axis is going to be at 90 degrees. So here the positive x-axis is where we have 0 degrees. Here we're going to have 90 degrees. So 110, it's a little bit past the 90 degrees. Yes, that's okay. It depends. Later on, when we get into vectors, we're going to have vector will be in one direction, and at some other point, we'll put another vector, and we'll measure the things with an angle. But we'll just take our perspective and we'll move it around places. So if we could look at the angle between 45 and 110, how big would that angle be? How many degrees are between the 45 and the 110? How many is that? 65. But that 65 degrees is not in standard position. That will be the measure of that angle between the 45 and the 110. That's 65, but those aren't in standard position. Standard position is really just saying that the positive x-axis is where we're going to put 0 degrees. And then we're going to say that is the positive direction. So if we have a 180-degree angle, where are we? I didn't follow the 7-second rule. I just wrote it down. 180-degree angle will be all the way over onto the negative x-axis. If I keep going, if I go all the way around here, how many degrees have we gone through? 270. Each quadrant has 90 degrees in it. So 90, 2 90s, 3 90s. And what's another word for 0 degrees? Or what's another name for 0 degrees? 360. How's that okay? Now we just labeled that one location, that 0 degrees, as also 360 degrees. And here's one of the fishy things about using angles for coordinates. There's a lot of different ways to describe a particular location. So if I have this angle here, I'm going to put it 45 degrees halfway through 180 and 270. If I start off at 0 and go counterclockwise, how many degrees do I go through to get that far? What's halfway between 180 and 270? $225? Because we could just take the 180 and just do 45 degrees more. So what's 180 and 45? 225. So we could say this is 225 degrees. Is that the only description that we have for that location? What else? What's another way we could describe 225 positive degrees in standard position? What if we went backwards? What if we started off at 0 and went backwards? What would another name for this location be? Negative 135 degrees, because here's negative 90. This is negative 180. And this would be negative 270. Now we're in the upside down. We have multiple names for all these locations. Good news, we have multiple names for all these locations. Bad news, we have multiple names for all these locations. How many names do we have for each of these locations? Infinitely many, because we could just go around the circle a bunch of times. So here I went around, I'm out of colors. Here I went around and did 225 degrees in the positive direction. But what if we miss the off ramp and just have to go all the way around again? So we did 225, and then we did another full circle. How much is that? 225 and 360. 585. So we could also say that this angle is at 585 degrees. That would be a little bit weird, but they do describe the same location. The best ones would be 225 and negative 135, positive 1 and a negative 1. It'd be really weird to call it 585 degrees. Extreme sports fans notwithstanding. Yes. Yeah, totally, it could come up. How's that? Yes. So it could be, mainly we're going to want to break out of degrees as well and describe, make our trig functions apply to real numbers. And the reason that we're going to want to do that is that the graph of a trig function is going to be a wave. It's going to go up and down and up and down. And there are a lot of things that we encounter that have a graph that goes up and down and just kind of repeats and repeats. Here, we're looking at things repeating. We go from 0 to 360, and then 360 to 720 is just another copy of what we just did. And then from 720 to 720 plus 360 is just another copy of what we just did. 1080? See, you can tell I don't watch extreme sports because I would have known that. That's like 3. So it could happen. It doesn't happen often when we're thinking in degrees, but once we start thinking in radians, then it's going to happen all the time. And instead of adding 360, we'll be adding 2 pi because we wanted to make it super inconvenient. Any questions? Yes. That means coordinates of x and y would both be negative. but the angle itself has a positive representation and some negative representation. The angle is positive. The coordinates might be negative, right? So in the first quadrant, here's what that question was about. In the first quadrant, our coordinates, our x coordinate is positive and our y coordinate is also positive. In the second quadrant, what are the x coordinates going to look like? The x coordinates will be negative, but what about the y coordinates? Positive. So in the second quadrant, words tricky. X coordinates are negative, y coordinates are positive. In the third quadrant, what are the x coordinates? Still negative. And what are the y coordinates? Also negative. Sleepy. In the fourth quadrant, what are the x coordinates? Positive, and the y coordinates? Negative. So x's are positive in 1 and 4, y is positive in 1 and 2. This is why counterclockwise is positive, because we said right is positive and up is positive. So all the positive shit happens in this first quadrant. So they go, we need to go that way to make things positive. There's nothing sinister about it. So first quadrant caffeinated, third quadrant sleepy, second and fourth quadrants they're winking. I think they're winking at each other too. I need to draw this comma backwards and then it'll look like they're looking at each other. And two will be like, oh, hey, Four, I see you down there. And Four will be like, oh, I see you up there too. All right. Any questions, comments, deep thoughts? This is called standard position. What we want to think about is what we're moving towards is a way to describe locations, not just with two distances, horizontal distance, vertical distance, but with an angle and one distance. So where this is headed instead of having a location just described by horizontal distance, vertical distance, I'll say we can also locate this point by going one distance and then turning at an angle, or turning at an angle and then going one distance. That's our goal. That's not the only goal, but one of them. We say, oh, this distance is R. And so we go R and turn through an angle theta. And so we could also describe this point with R theta. If we're going to use angles to describe locations, we have to have a zero location, and we picked the positive x-axis. Like I was. Questions? Comment? Polar coordinates. Instead of having an origin and an x-axis and a y-axis, we have a pole, and we're measuring a distance through an angle. We always list it R theta. That's the way that we're going to list things, the distance, then the angle. But really, we could think of it as starting off facing the positive x-axis, turn through an angle theta, and go the distance R. Still using two numbers to describe one location in two-dimensional space. Two-dimensional space will always require two numbers to describe that location. That's why mailing addresses are such a pain in the ass. You need like 3 numbers, sometimes even 4. Street, a house number, maybe an apartment number, and a zip code. And we have work addresses too, so then it's like, that's like 8, because that's actually 9, because there's 4 for work. And then there's like a 5th one that describes the time that you're at that second location. All right. This is angles in standard position. This is where chapter 2 picks up. The idea is we're taking what we know about acute angles and we're going to expand it out to angles that are bigger than 90 degrees. Let's take a break for a little bit and we'll come back and let's start at 2:05. And then we'll just go to 3 o'clock if need be. So come back at 2:05 and we will start practice test 1. For those of you just playing along at home, thanks for playing.